source chooses 0 or 1 with equal probability. The sender sees that input bit. The receiver sees only the channel output and knows that this gate flips each input independently with probability 1/10. Before the output arrives, the receiver is missing one yes or no answer. Was the input 0 or 1? We call that one missing answer 1 bit. After the output, some of that uncertainty may remain. We score the channel use by how much of the missing answer disappears on average. The output is correct 90% of the time. Does one use convey close to one whole bit, close to half a bit, or do we need another measure? Lock in one answer before we inspect the receiver.
I choose close to one whole bit. If the output is correct 90% of the time, it seems as though we lose only a small part of the original answer.
Trace one case. The receiver observes output 1. A true input 1 takes the matching branch with probability 0.9. A true input 0 takes the flip branch with probability 0.1. Because the two inputs were equally likely, the receiver's updated chances are 90% for input 1 and 10% for input 0. Updated chances after seeing an observation are called a posterior. The receiver is usually right, but is not certain. Measure the remaining ambiguity with the same ideal surprise bills used for a source. The likely input contributes 9/10 times the negative base 2 logarithm of 9/10. The unlikely input contributes 1/10 times the negative base 2 logarithm of 1/10. Add the two terms. The remaining uncertainty is about 0.469 bits. Output 0 leaves the same amount. Averaging over both possible outputs therefore still leaves 0.469 bits. This average uncertainty after the output is called conditional entropy. Before the output, one yes or no answer was missing. After the output, 0.469 bits remain on average. Subtracting gives 0.531 bits per channel use. This average reduction in uncertainty is called mutual information. 90% is symbol accuracy. 0.531 bits is the expected uncertainty reduction about the input. Both statements describe the same experiment, but they use different scales and answer different questions. Keep the 10% flip gate. Input 1 now occurs 10% of the time. Does the channel still convey 0.531 bits per use? Choose same or lower.
The physical gate did not change, but the source has less uncertainty to begin with. I choose lower.
Trace output 1 again. A true input 1 followed by no flip occurs with probability 1/10 times 9/10, which is 0.09. A true input 0 followed by a flip occurs with probability 9/10 times 1/10, which is also 0.09. Those two roots are equally likely. After observing output 1, the receiver now faces a 50-50 posterior, not the earlier 90-10 posterior. Before any output, this biased input has about 0.469 bits of uncertainty. Average the uncertainty left after both possible outputs, and about 0.258 bits remain. The channel therefore conveys about 0.211 bits per use. The physical gate stayed fixed, but the starting probabilities changed both the posterior and the mutual information. For this symmetric channel, the balanced input gives the largest mutual information. That maximum is called capacity. Next, we will ask why this statistical maximum becomes a speed limit for reliable communication.